Looks like we got quite a crowd today, and we can get it started. So, hello everyone. Welcome to the Space Activity Seminar. I'm Shirley, the host of this meeting, and Kevin, as he mentioned in the email, he's out today. And so our featured speakers today is Rocketry at Virginia Tech student design team. So the title of the presentation shown on the slide is Hybrid Rocket Motor Research and Development. I believe we'll hear about some high-powered stuff of their recent development with motor designs and future investigations on the path to launch. So the floor is yours, Ben, and some others in the team.
Awesome, thank you very much. Welcome everybody. Thank you for coming to our presentation. We are the propulsion sub-team for Rocketry Virginia Tech, and today we'll be presenting some of our work in the research and development of a hybrid rocket motor. My name is Ben Piper, and I'm the propulsion lead, and presenting with me today will be Anthony Spinetta, Salmet Gunnapanidi, and Zachary Hulsher. So every June, Rocketry Virginia Tech competes at the Spaceport America Cup in New Mexico, hosted by the Experimental Sounding Rocket Association, or ESRA. Collegiate rocketry teams from around the world compete to fly their rockets as close as possible to their target apogee, which is either 10,000 feet or 30,000 feet. Teams also have the option to either buy a commercial motor or design and build their own. These two categories are called commercial off-the-shelf, or COTS, and student research and developed, or SRAD. The category we will be competing in June 2022 is a 10,000-foot commercial off-the-shelf solid motor. But our goal for June 2023 is to compete in the 10,000-foot student research and developed category with a hybrid rocket motor. So what is a hybrid rocket motor? As the name implies, it is a hybrid between a solid motor and a liquid motor. It utilizes a liquid oxidizer, which, as you can see in the diagram, sits at the forward part of the motor, and a solid fuel grain, usually made of a hydrocarbon, such as paraffin or some type of plastic. The solid fuel grain has a cylindrical hole cut down the middle of it that the oxidizer will be injected through. When ignited, this is where the reaction occurs. The oxidizer and the fuel grain together will burn the grain outwards. This combustion reaction is what will be shot out of the nozzle, producing thrust. The benefits of a hybrid motor over a solid, which is comparatively much easier to develop, is that hybrid allows for in-flight manipulation of the thrust. Once a solid motor is ignited, it will behave as it was casted to. With a hybrid, the mass flow rate of the oxidizer heavily influences the thrust produced by the motor, which can be controlled by the injection throat diameter. This is the current CAD model for our proposed hybrid motor. It has the same basic components as the diagram on the previous slide, these being the oxidizer tank at the forward part of the motor, valving to inject the oxidizer into the combustion chamber where the fuel grain is sitting, and a nozzle to produce the thrust. When it comes to choosing different fuel components, the team decided to use nitrous oxide as the oxidizer for a couple of reasons. It met ESRA's requirement for being non-toxic. It has industry use in hybrid motors, meaning we can compare our test data to theirs. And probably most importantly, nitrous oxide is self-pressurizing. This means that some nitrous oxide will boil off from its liquid state, creating pressure at the top of the tank. The pressure will force the nitrous oxide through the valves once it is opened, and will help to prevent the reaction from moving its way back up due to the pressure created by the combustion. The graph on the left shows the expected pressure of the oxidizer tank and combustion chamber over the course of the reaction. The graph in the middle shows the relationship between the mass of the oxidizer and the impulse the motor will produce. For the solid fuel component, the team has decided to use 3D printed ABS plastic. There were other options, such as 3D printed PLA plastic, as well as casting a grain out of paraffin wax. ABS was ultimately chosen due to giving the team the ability to design a very specific internal geometry, leading to precise control of the regression rate of the fuel grain, and finally giving the team control of the thrust curve. After reading studies from researchers on this topic, the geometry on the right was chosen. The shape allows for the surface area to stay roughly the same, meaning the thrust curve will be more consistent and will create less in-flight loads on the rocket structure. The helical port structure was implemented to help increase the regression rate of the fuel grain due to higher skin friction between the nitrous and the fuel grain. Every small change that is made in the geometry of the fuel grain can change the thrust curve. There's a lot of potential for more research with different fuel grain geometries and materials in optimizing a hybrid rocket motor. The oxidizer tank was designed with the goal of being able to carry 27 pounds of nitrous oxide, as that was determined to be the optimal amount from our simulations. The tank has an outer diameter of 6 inches, a 1/4 inch thick walls, and 48 inches long. It is made of 6061 T6 aluminum, which is compatible with nitrous oxide and is light yet sturdy compared to other metals. The end caps, as seen on the right, are bolted into the ends of the tank and have a clearance of 1/1000th of an inch. O-rings are slotted into the grooves of the caps to ensure the seal of the tank. This tank has been pressure tested to 1500 psi, while its maximum expected pressure is only 1000 psi. While this is not the most optimal way to make a tank, it was designed to be modular with potential future designs. The end caps can be taken off, and different length aluminum cylinders can be replaced in the middle at a low cost. It also allows the motor to be tested outside of the rocket structure and then integrated later. The combustion chamber is an Aerotech 98mm motor casing, which is designed to withstand the heat and pressure of a rocket motor firing. The fuel grain will sit inside the combustion chamber, and nitrous oxide will be injected into the combustion chamber through valves connecting the oxidizer tank previously seen to this combustion chamber. I'm now going to pass it over to Zachary to talk about the nozzle.
All right, so if you've taken an introductory course in propulsion, you'll know that the nozzle is core to the physical process that enables an engine to work. So essentially what a rocket engine does is you combust your chemical propellants, and so you convert that chemical energy into thermal energy. And what you want to do is you want to convert this into kinetic energy. You want this mass to move as quickly as possible so you can get a decent specific impulse. So what we do is we take the hot gas, and then we have a constricting throat. And then when this chokes, the flow is moving at Mach 1, and then we expand that again to then accelerate that past Mach 1. And that's a converging diverging nozzle. There's really two types of these that we could do. We could have a conical nozzle, which would probably have a half angle of about 15 degrees. And that's simple to machine, but a bell nozzle is a little bit more efficient because you don't have as great of a component of the velocity that's going perpendicular like this. And graphite will be used for this because we can have that machined and it will tolerate the temperatures we're working with. And this is something that will be sized following repeated static firings that will enable us to optimize this.
Great, thank you, Zach. The plumbing section is kept closed by a motorized ball valve that will be opened when our software team gives the launch command. At that time, nitrous will flow through the plumbing and into the injector plate as seen in the middle picture. The purpose of the injector plate is to atomize the nitrous oxide, making it react with the fuel grain easier. The number and shape of orifices on the injector plate are determined by MATLAB scripts that were written and will be seen later. Another of ESRA's requirements is to be able to fuel the rocket remotely. To accomplish this, a quick connect valve will be accessible through a small hole in the body tube and can be connected via a linear actuator, and then disconnected when fueling is complete. Nitrous will be filled in 30-second intervals to allow pressure to build in the tank and to allow venting of gases from the tank prior to fueling. These 30-second intervals are also to ensure that the solenoid we are using does not burn out from being active for too long at any given time. At the forward part of the oxidizer tank sits our abort valve system. This is also controlled by a motorized ball valve that our software team can use to vent excess pressure during the fueling process. There's also an emergency mechanical pressure relief valve that can be set to a specified pressure, and when that pressure is reached, it will vent until it is below that pressure again. This valve is set to 1000 psi, as that is when nitrous oxide can become unstable. I'll now pass the floor over to Anthony and Salman to talk about our ignition system.
In traditional high-power rockets with lower-class motors, a standard E-match can be used to initiate the combustion process. However, our ABS fuel grains are very energy dense, requiring a much higher activation energy to achieve vaporization. Therefore, an E-match cannot be used with our hybrid motor design. Instead, we are designing and implementing an ignition ladder that consists of an E-match that will light a segment of a 54mm solid fuel rocket motor. The ignition puck, as shown in two of the figures, is friction fit inside of the fuel grain, and an ABS puck stopper is utilized to prevent the ignition puck from falling into the pre-combustion chamber during testing. To ensure that enough activation energy is produced, the top surface of the ABS fuel grain will be lightly coated with quick dip pyrogen, a coating that is used for creating motor starters. The ignition puck will be tested with various thicknesses in the presence of an ABS fuel grain to ensure that it can successfully vaporize ABS. Secondly, the system will be tested in the presence of nitrous oxide to gather data regarding the performance and reliability of the ignition system.
Thank you, Anthony. Our motorized ball valves are controlled remotely by our software team. To make this happen, the team utilizes multiple BeagleBone blacks, which will send pin signals that our PCBs will interpret and thus control the motors. These are used to control four main components: the main injection ball valve, the abort ball valve, the solenoid that controls the fill cycles, and the linear actuator that disconnects the external tank from the vehicle. The software stack is built using ROS, or Robot Operating System, and utilizes a node architecture. This means that various motor drivers and sensor readers are nodes within the software, which helps the team concurrently control the different components without blocking each other. Our procedure for launch will all be controlled from our software team, while we are all 2,000 feet away from the vehicle to ensure safety of all personnel. The launch procedure will begin with the filling and pressurization of the oxidizer tank from the external nitrous tank. Once the tank is filled to the appropriate level, the external tank will be disconnected from the vehicle and the pressure will be monitored until it is roughly 750 PSI. At this point, and with the go-ahead from faculty and designated safety officers present, the nitrous will be injected into the combustion chamber, and very shortly after, the ignition puck will be ignited to begin the reaction. I'll pass it over to Salma to talk about our test stand.
All right, so a code flow is a test that is performed on rocket engines to validate the structure of the system. Specifically, a code flow is important as it allows us to see how our oxidizer tank and plumbing perform at low temperatures and high pressures. Following a code flow, a static fire test is usually performed. This differs from a code flow as it involves the ignition of the engine, which results in significant thrust being produced. A static fire test is extremely valuable as it helps us in analyzing our system in conditions that are very similar to those during flight. In order for us to repeatedly conduct these tests, a code flow and static fire test stand was developed in the past. However, this code flow and static fire test stand was redesigned so that the oxidizer tank can be more securely mounted to the stand for testing. As shown in the assembly on the far right, this stand does not have any moving parts and thus should allow us to more reliably run repeated code flow and static fire tests. The image in the middle is a side view of the lower mount for the oxidizer tank, where the oxidizer tank sits on top of a load cell rather than hanging from one, which would reduce any motion in the system and thereby produce more accurate and reliable mass flow rate data. Now, speaking of mass flow rate, the image on the far left is a sample of data recorded by a load cell in a previous code flow. We will be using similar data from future code flow tests to calculate the thrust of our motor. Finally, the shown test stand is specifically designed to hold an oxidizer tank, but it will later be integrated into a static fire test stand so that we can connect a combustion chamber to the existing system and run static fire tests.
Thank you, Salma. And now back over to Zachary, who will be giving an in-depth explanation of our models.
All right, so whenever you're designing something, you have to be able to model it in order to size parts and know how it's going to behave. When we're designing this engine, we have to say, is this going to be adequate to put the rocket at the altitude that we want it to? In order to do that, we have to be able to simulate it thoroughly. So our sim is divided into two portions, the liquid and the vapor phase. Now, this is because we have nitrous in our tank that is continuously vaporizing. And so in the beginning of our burn, we are combusting liquid nitrous. And then at the end of the burn, the vapor that was left in the tank at the end is what's combusting. And so we're still producing thrust, but there's less. And so that is the trailing portion of our thrust curve. And then it's also important to note that there are two components of our mass flow rate, is we have both an oxidizer and a fuel. The majority of the impulse, as I mentioned before, comes from the liquid portion of our burn. And we have approximately a linear mass flow rate curve in the liquid phase with approximately exponentially decreasing mass flow rate curve in the vapor phase. Now, the reason for this from a physical perspective is that when we're combusting liquid nitrous, that mass flow rate is determined by the change of the temperature of the liquid, which drops as it vaporizes. Whereas when we only have vapor in the tank, it's essentially driven by how much vapor is left in the tank. So then if you study differential equations, it's natural to expect that we get something that has this exponential behavior. And on the right, we then have a flow chart that comes from Rick Newlands, who's in his work is the basis of a lot of our numerical models. And as I said before, the temperature is essentially the driving factor here in the liquid phase. And this is essentially because the vapor pressure of the nitrous is determined by the temperature of the liquid. And so the difference between this the tank pressure and the chamber pressure is used to give the pressure drop over the injector, which then determines the mass flow rate of the liquid oxidizer. And that's determined using a formula that can, I believe, essentially be derived from Bernoulli's equation with a modification for an empirical loss coefficient in this formula. In the plot on the right, we show our sims using some sample values that shows the nitrous vapor pressure and the combustion chamber pressure. And so to give a little bit more detailed overview of how this works for the emptying of the liquid, we find the latent heat of vaporization and the specific heat capacity of the liquid from interpolating a set of values for nitrous. We then find this change in heat here. And then from that, we can get the change in temperature, and we iterate this. And then you interpolate for liquid and vapor densities, as well as the vapor pressure. And you find the oxidizer mass flow rate, the quantity of nitrous that vaporizes on that time step, and then you update the mass in the tank, and you repeat this until you have no liquid left. Now, it's important to note that essentially what's happening here, the reason why the temperature of this liquid drops is that it's boiling off. So you have a liquid that's changing phases to a gas, so you have to pull energy out of the liquid to do that, because the gas molecules are moving faster than the molecules in the liquid. And so it is important to say, well, yes, there is some heat that then goes through the tank walls into the liquid, but our burn is relatively short. So the amount of energy that goes through the tank walls is negligible. So essentially what happens is heat gets pulled out of the liquid, and so the temperature steadily drops as the tank empties. And as I said before, it's not just the oxidizer mass flow rate that we have to worry about. We also have to say, what is our fuel mass flow rate? And that's essentially tied to how quickly is our plastic fuel vaporizing. This is determined by the regression rate, which is determined by the oxidizer mass flow rate that we're continuously finding. So you can use the fuel density, the burn area, and the regression rate to determine your fuel mass flow rate, which then naturally connects to, as Ben was talking about, how the geometry of this fuel grain is, that has a very strong influence on our thrust curve. And so our regression rate here is given by A times this flux term to the power of G. And A and B are empirical constants that are determined for the fuel that you're using. And so G is your oxidizer mass flow rate divided by your port area, where that port area is constantly changing while you burn fuel because it's expanding over time. All right. And so our flame temperature, gamma, which is the ratio of specific heats at constant pressure and volume, the molecular weight, et cetera. These things are determined from propep. And the simplest way to determine these sorts of things is essentially through an enthalpy balance, where you have your products and your reactants, you have a change in enthalpy, and that is equal to the integral, I believe, of your specific heat taken at constant pressure from your start temperature to your end temperature. Your end temperature is your flame temperature. And then you can take into account dissociation reactions and so on. ProPEP, I believe, also includes minimization of Gibbs free energy, but it does all of this for us. It calculates these values, and we can feed this into our sim. And then we can get things like our exhaust velocity, which can be given by this formula down here below. And we use our exhaust velocity, our total mass flow rate, and of course, the pressure to give the pressure thrust component to give our thrust. And this plot on the right shows a sample run with some sample inputs. So you can see there's a linear portion and approximately an exponentially decaying portion here. And so now ultimately the best way to validate this sim, it can't just make sense from a physical perspective. You have to say, are my assumptions valid? And the way you do that is you compare that to experiment. And so a large part of why our cold flow is important, there's really two big reasons. Number one is you have to determine the empirical loss coefficient for our system, which we determined in this recent cold flow. And then you also have, and then you can say, are my models valid? How does my system perform? And so here we show a fit, and that shows how close our model's prediction is to our empirical results. And they're very, very close. And then we also have a video of our cold flow as well. And so this is just nitrous oxide is flowing through our injector. And we did this out at Kentland Farms, I believe, this past May. That was a great way to test all of our launch control systems as well, because our software sub team had to run this from a distance. And that was, of course, was a big technical challenge for the team.
Oops. Sorry, there we go. Awesome, thank you, Zach. That is everything of note that we have done up to this point, but there's still many applications that this hybrid motor can explore. The geometry of the fuel grain is a big factor in determining the thrust curve of the motor. Some of these parameters, including shape, helical rate, and port area. Researching different fuel grains to create a very specific thrust curve could have numerous applications in hybrid rockets. An example could be designing a thrust curve that has a very high initial thrust to meet the minimum off-the-rail velocity requirement, but then decreases as to not change our expected apogee. Researching different materials for fuel grains could also prove to have benefits for hybrid motors. How the fuels affect the total impulse of the motor gives a lot of options to anyone designing a hybrid motor. Injector plate geometries also have a very large impact on the mass flow rate and the regression rate, and thus the thrust of the motor. The picture on the left is a side view of a proposed injector plate. Having a different number and angle of orifices would be a very interesting study that Rocketry Virginia Tech hopes to conduct over the next few years. Health monitoring systems is also something that the team hopes to implement. This would include pressure sensors that, in the event of an in-flight anomaly, could automatically shut off the motor in hopes of saving the system from catastrophic failure. Throttleability of our hybrid motor would also eliminate the need for any type of altitude adjustment system. Currently, the team utilizes an active drag system that deploys flaps perpendicular to the vehicle that will bring the apogee down to the target of 10,000 feet. Onboard computers determine how far and for how long to deploy the flaps to ensure the correct apogee is reached. The hybrid motor could utilize the same type of onboard computers, but instead it would be controlling the ball valve for the main injection and decreases the thrust as needed to hit our target apogee. So this concludes our presentation. At this point, we'd love to open the floor up for any questions that anyone may have.
That was a great presentation. Very impressive amount of detail and in the analysis. Just very interesting to watch that. You guys are doing a great job. I really appreciate it.
Thank you. We appreciate it.
Thank you.
I was interested in that video and the testing you did. So, right, there was no motion in that. So you had some sort of facility where you could keep the rocket still. Is it buried in the ground? Is it going down? I'm just curious what the testing is like and what the safety issues are. And I mean, I know what they are, but how do you handle them?
Sure. Yeah. So in this test specifically, we just have our oxidizer tank. It's not integrated into the rocket. So our oxidizer tank is, it's a little hard to see. Right here is, I don't know if you can see my cursor, is hanging from that was our older test stand. It's hanging from a load cell, and that's how we were able to measure our data. But it's hanging here. We are all way back here by this building controlling it. So our software team is sending the commands to open the valves. And when they give the command, the ball valve opens. And this right in this testing setup, there was no this was a cold flow, so there was no combustion. There was no our fuel grain was not implemented. Nothing was being ignited. So our injector plate is staked down right here, and it's then propelling all of the nitrous oxide out of the tank sideways here. So for this testing, there was very little thrust being produced, so we didn't have to have a very robust test stand. But for our future testing, we do plan on integrating the combustion chamber and igniting. So we're building let's go back to that test stand slide. This one here, so our test stand is more, our oxidizer tank is better mounted, and then this will also be used in tandem with a test stand for the combustion chamber that will be thrusting. It'll be upside down, so it'll be thrusting into the ground, and the plume will be going into the sky, so that it won't hopefully not be going anywhere. So.
Okay, no, I'm very interested in that. And you mentioned at the end, right, the active control plans that you guys have. So can you say what it'll be like to build systems to work in that environment, right? You're going to be measuring temperatures and pressures. Kind of an interesting place to put those sort of sensors.
Right, exactly. Yeah. So for both things, the health monitoring and the throttleability, having pressure sensors and temperature sensors inside the combustion chamber and the oxidizer tank that would be relaying like live data would definitely be something that we hope to implement soon. And that we could automate, write scripts for that would interpret this data as it's happening and would require no human interaction. And if we see there's a pressure spike in either the combustion chamber or the oxidizer tank that could cause any kind of catastrophic failure, we can have it set to just cut the motor at that point, close the ball valve, stop the oxidizer from dumping or injecting into the combustion chamber, essentially cutting off the reaction. And when you stop the reaction, hopefully that will be soon enough to bring the pressure down and prevent any kind of failure like that. And then for the throttleability, the same thing could be used. We can use some type of onboard computers and altimeters to determine our current velocity, acceleration, and altitude, and then use that data with to determine how much more thrust we need to hit our target apogee. And then the goal would be to design the rocket so that would reach maybe 10,500 feet, and then as it's going, it'll keep checking this iteratively, and it'll then determine how much to cut the thrust down as it's going up, and then hopefully we'll bring it down right to 10,000 feet. So
okay,
that would be.
I've known that they could put sensors in rocket motors, but I just always imagine that's a really sophisticated, military grade device. Is it straightforward to get devices like that can operate in that environment?
It was my understanding that it wasn't that difficult. Zach, are you more familiar with this than I am?
I'm not familiar with what sensors are available. I would imagine, at least from a throttling perspective, we could probably get a lot of the information we would need by if we can measure the pressure in the oxidizer tank, and then we can model our motor properly from that, and we can, if we can have readings on, say, how high the rocket is, how fast it's moving, that would probably be enough that if we can test it over and over, we can throttle it from that, because we just need to control the ball valve. But I'm not familiar with what sensors would be available for putting those into the combustion chamber.
We currently have sensors in the oxidizer tank to measure pressure. And then we also hope to add a second one that'll also measure the temperature. And then for the combustion chamber, it's a little bit warmer there, but it should still be doable.
Okay, so it's not as extreme of an environment that you need, right? It's easier than what I was thinking.
I believe so, yes. There were plans written up for this. We have documentation on it. Unfortunately, I don't know it off the top of my head. But plan procedure for implementing this.
Throttling is still a ways away. We need to static fire this year and then would fly it this upcoming year, and throttling would probably come after that. So likely be after we graduate.
All right.
Yeah, this will hopefully be a multi-year. I mean, it's already been a multi-year project, but the research on this can be done for years after we graduate. So
yeah.
Well, I'm not a motor person at all, but I've been working with sounding rockets for a long time. And the Bristol Aerospace is the maker of the company for all the motors I've used. And I know they're still learning. We had an interesting thing where they came up with their Mach 4. This is probably 8 or 10 years ago, a new motor, and they changed the nozzle diameter because a certain part was hard to get, and then all the sounding rockets started to fail. And eventually the way they described it was the older people who had originally designed that rocket retired off. And so now some new people made some changes to an existing design and didn't have all the lessons learned. And so they had to relearn some things. So even rocket motors may seem simple, but they're not. There's a lot going on in there.
Yeah, no, that is something that we currently have that we're dealing with. A lot of our alumni were the ones who initially pioneered this idea. And so we're very fortunate. We have a very strong alumni network. We reach out to them very frequently, and they're very willing to help us out, give us some of their advice and their thought processes behind what they were doing. Even though they're working 9 to 5s now, they still make time out of their days to maybe explain why they made some decisions, so that we can, if we do want to change something, we understand why they made that decision in the first place and make sure that we're not going to do something that they had already accounted for.
Okay. Do you get any help from Wallop's flight facility?
Not that I'm aware of. I don't think so, Zach.
I'm not aware of that.
No.
I think there's people there that would be happy to give you advice.
Yeah, that would be fantastic.
Yeah, some of them are on our industrial advisory board. Maybe
Really?
if you
Okay,
guys are up
cool.
for it,
Yeah.
give a short presentation at one of our upcoming meetings. Is
that
Kevin
would be awesome.
Chimpaw, do you report to Kevin Chimpaw, or who's your technical advisor?
Yep, Kevin Chimpaw.
All right, let's email him, and he's giving a presentation next week to the IAB.
Right, yeah.
Maybe if you guys had a few minutes of that, maybe him representing you or you doing it yourselves. There's people from Wallops there that might be interested in this. I'm sure they would like to be advisors for you guys.
Sure. Yeah, he actually, I think he told us about that, and he asked for just some slides and some speaking notes for him to, I think, to present on our behalf at that meeting. So, but we'll definitely make sure to give him everything he needs to hopefully make us look good. But
yeah, but also, you know, right, the point of the whole reason we talk to those guys is to get help from them.
Right. Exactly.
You know, make a request for some involvement, part of that.
Sure. Yeah, we'll include that for sure. Yeah, we are always open to expert opinions, so that would be great.
All right, sounds good. Great job, guys.
Awesome. Thank you very much.
Mhm.
Yeah, thank you for a great talk and a great discussion. Good job. Anyone else have any comment or questions? Feel free to unmute yourself.
Okay, I just did that. Yes, very nice presentation. I have a question about your thrust curve.
Sure.
You know, I understood that in transition between phases. It looked to me like there's actually 3 stages to this. You know, quasi-linear, I guess that's the liquid burn. Exponential, that's the vapor burn. But how about that abrupt transition? Do you understand that in physical terms?
And the abrupt transition, I assume, is when you originally run out of liquid, but I'm not sure off the top of my head why the slope looks roughly linear at the beginning of this exponential portion.
Linear meaning, you know, almost vertical.
Yes, yeah.
You know, yeah, it almost looks like there's a cutoff of the first burn mechanism. One might have expected a more gradual transition if things were continuous in terms of the burns tapering off, one tapering off and the other taking over.
Yeah, that's something we can definitely look into further.
Zach, do you think it could have something to do with the time step size in these simulations? Maybe just
it's possible.
Okay, yeah, something like that. So, but hopefully through more of our physical testing, we can improve these simulations as we go. We have already validated some of our, I believe it's on the next slide. Our mass flow rate simulation is really, really close. So to what we predicted. So hopefully, as we do more testing, we'll be able to make these simulations even better.
Yeah, well, I've got the floor. Could you explain the function of the abort motor? It seems
sure.
Self-explanatory, but how does that come into the planning?
Yeah, sure. So the abort valve system it has 2 main reasons. One, as an emergency, you know, if we're overpressurizing, nitrous oxide can become very volatile around 1,000 psi, I believe. So we need to make sure that we're closely monitoring that, and we have pressure sensors in here feeding live data so we can watch it as we're filling. And so the motorized ball valve can be controlled by the software team. And so while the tank is being filled, there's already gas, just ambient gases in the tank. And so while it's being filled with nitrous, we need to release that ambient gas that's in there to make room for more nitrous as we're filling. So that's why part of the reason why we fill in 30-second cycles. So we fill for 30 seconds, we wait, we let some of it pressurize, and we just crack the abort valve very, very slightly, and it just lets some of the ambient gas out of there. And then once we have filled the nitrous tank to enough, I believe it's about 15% ullage, that is left at the top of the tank for just pressurized gas of nitrous vapors. Then we stop venting and we just close it and let it pressurize. We monitor the pressure until it's about 750 psi. And at that point, there's enough pressure from our simulations to determine that we can open the main injection and there will be enough pressure to force all of the nitrous into the combustion chamber. We need this pressure at the top. Now, you might be thinking the motor is mounted vertically, so gravity should be helping us, moving the nitrous down. But we also need this back pressurization to prevent any reaction from the pressure created from the combustion to force the reaction back up into the tank, which would be very bad. And then also we have this mechanical pressure relief system. I believe I have it in my room actually, but all it does is it's a little plate with a spring, and you can screw it down further to resist more pressure. And so you can set it to whatever pressure you want. And once it hits above that pressure that you've set it to, it'll push the plate open and start releasing pressure until it's back below that threshold, and it'll close again. So we can set that to around 1,000 or probably a little bit just below it, just for safety reasons. And that will prevent any chance of overpressurization in the tank, because it'll just release it as it's getting too high. I hope that was a somewhat better explanation. If you have any other questions, please ask.
Hey, really quickly, I just wanted to mention, so my name's Hannah. I'm also a member on the team. If you go back real quick to like the thrust curve that he asked the question about, yes, the reason why there's such a sharp drop is because you end up running out of liquid nitrous at that point. And since all that's left is gaseous nitrous, it's much less dense than the liquid nitrous, which ends up causing a really sharp drop in the mass flow rate, which then also affects the thrust curve, which is why there's such a sharp transition there.
Great, thank you, Hannah. Yeah, I was thinking it could be something like that, but I didn't want to provide false information.
Any other questions or comments from the students, maybe? Okay, looks like I'll probably just count to 3, just in case.
Sure.
1, 2, 3. Okay, you lose your last chance. So anyway, I think you guys can reach out. There's some contact informations, and
Yes, please.
Yeah, Google around the Rocketry at Spaceport VT. You can find their website. I think it's a pretty cool one. There are plenty of opportunities and teamwork as well. So if there's no more questions or comments, I will call it the end of this presentation. And I'd like to thank our speakers again for the wonderful presentations, and I give you guys a round of applause.
Thank you very much. We really appreciate it, this opportunity to present some of our work. Yeah,
great job, guys. So I think the next seminar will be at the same time on November the 17th. I think we're here about quakes on Mars, which also sounds very exciting. So I will probably see you guys in 2 weeks. So bye, everyone.